Okay, in this lecture, we will start chapter 5, which is a closer look at instruction set architecture. What is instruction set architecture? Of course, we know what is instruction set architecture. Is the layer that convert the like a high level language like C, Java, Python, or any other language to machine level language. What is machine level language? In chapter 4, we already discussed machine level language for multiprocessor, and each processor has its own machine level language. These machine level languages are different. So if let's say we have four processor here, 1, 2, 3, for example. Processor number 1, CPU number 1, CPU number 2, CPU number 3. Each of these CPUs, they have their own machine language. Okay, machine language 1, machine language 2, and machine language 3. They don't understand each other. Okay, they don't understand each other. They only understand their own machine language. So if you feed CPU number 2 with the machine language of CPU number 1, there is no relationship, there is no communication. Okay, there will be no link between CPU 2 and machine language 1. So what does it mean? Does it mean that every time we are writing a program in C++, do we have a write our program for machine CPU 1 in a different way? We write it for processor 2 and processor 3. So should we consider the type of our processor when we write a program? Of course, we know that the answer is no. We don't care about the type of the processor. We don't care if the processor is AMD, it's IBM, it's Intel, or any. We write our language in C++. Okay, so what or who is responsible to take care of this problem? Between the hardware and software level of each processor, there is a layer. Okay, this layer is ISA. Okay, so this layer, each processor has this layer. This layer understands the high level language. Okay, high level language, and translate that language to the machine level language corresponding to the processor. So ISA translates the high level language to machine level language 1 for CPU 1. ISA 1, for example. ISA 2 converts or translates or compiles the C++ to machine language 2. Is it clear? I think that it should be clear because we have something called ISA, which translates any high level language to machine level language. Any question? Okay, we want to discuss the different types of like instruction sets and instructions. Okay, so if you remember, for multiprocessor, we had instructions with 16-bit length, which had 4 bits for opcode, and 12 bits for address. Okay, do all other processors work in the same way? Of course, no. Okay, so we want to discuss like a different type of these instructions. So objectives of this lecture of chapter 5, we want to understand the factors involved in instruction set architectures. So we want to discuss the factors involved in instruction set architecture design. Okay, so what factors are involved? Also, we want to discuss different memory addressing mode, because in microprocessor we had two different addressing modes. If you remember, we had, for example, load and load I, if you remember, indirect addressing and direct addressing. But there are more types of addressing. And finally, we want to see how instruction level pipelining can help to improve the speed of our processor. Okay, so instruction level pipelining. So we want to see how does this pipelining can improve our performance. Okay, so we are going to have a detailed look at different instructions format, different instruction formats. Here is the instruction format for microprocessor, but we are going to look at different instruction formats, operand types, and memory access methods. Okay, so we are going to present this information. Okay, so how the instruction sets are differentiated. How they are differentiated. Okay, so the instruction sets are differentiated by number of bits per instructions. So number of bits per instruction. For Mario processor, we had 16. So different processors have different number of bits per instruction. Then the second differentiation is the instruction stack based or register based. Okay, we will talk about the stack soon. So is the instruction stack based or register based? The next one, number of operands per instruction. In Mario processor, we had only one operand per instruction. For example, add X. We have only one operand. And what does it do? It adds X with the accumulator and stores the result in accumulator. Okay, so number of operands per instruction also is another important factor. The next one is like the operand location. Operand location in the instruction. So if this is the instruction, where is the operand? Is the operand here? It's operand. It's here. It's here. It's here, or it's here. Or if we have two operands, are we going to store them, these operands, here and here, or here and here? So it depends. So the location of operands is very important. Then the next differentiation is types of operations. What type of operation are supported by these instructions? For example, for microprocessor, we have add or subtract. Can we multiply? Can we divide? Can we factor, or any other operations? What different type of operations do we have? And finally, type and size of operands. Okay, so type and size of operands. Okay, so how many bits is each operand? Okay, so if we want to add two numbers, or what's the size of these two operands? Okay, these are the like different like instructions, but in designing an instruction we need to like have consideration, okay, which as I said are explained here. Okay, so in designing our instruction set, considerations are given to instruction length as a summary. So let me the considerations are given to instruction length is the length of instruction is short, long, or variable. Okay, the number of operands, number of addressable registers. How many registers do we have inside our processor that we can address them? We need to give consideration to memory organization. And finally, addressing mode, which we are going to discuss all of them one by one. Okay, so these are the consideration for designing a instruction. Okay, so before starting the like designing an instruction, I want to talk about byte ordering. Okay, because it's very important. Why it's important? Because sometimes the length of an instruction, let's say 16 bits, but the size of the memory, the length of each memory is 8. And if we are going to store 16 bits in 8-bit, we need to split it to two parts, significant most significant byte and least significant byte, and we store it like in two adjacent location in the memory. Now the question is that which one we should store first. Should we store LSB first and then MSB, or first store MSB and then LSB? Okay, so it's very important. So we should know what method we are using to store the data, and this byte ordering is called endianness. Okay, so byte ordering or endianness. Okay, so if we have 2 bytes, as I explained, the integer number, 16-bit integer number, can be stored so that the least significant byte is followed by the most significant byte, or vice versa. Okay, exactly as I explained. So what we should know about these orders, we have two different byte ordering. The first one is called Little Endian. So Little Endian, okay, and the other one is Big Endian. In Little Endian, the least significant byte is followed by the most significant byte. Okay, so if this is address 0 and address 1, okay, so first we put least significant byte and then most significant byte. Okay, this is Little Endian. For Big Endian, the most significant byte is stored first. So if we have two addresses, address 0 and 1, first we store more significant byte and then we store least significant byte. Okay, so it's different. When we design a machine, we should know which one we are going to use. What's the difference? There are pros cons for these two designs. Okay, we will see it soon. So if we have, let me just show you an example. Big Endian, Little Endian, and here is the address. So address 00011011, and we want to store this number. What is the number? The number is hexadecimal 1, 2, 3, 4, 5, 6, 7, 8. We want to store this number in our processor. Okay, and let's assume each address can store 1 byte. 1 byte. So 1 byte is 2 hexadecimal digits. We know that. Okay, 2 hexadecimal digit is 1 byte because each hexadecimal number is 4 bits. Okay, so in Big Endian, what we do, we take first we start from the most significant byte. So 1, 2 comes to lower address, then 3, 4 here, 5, 6 here, and 7, 8 is here. Okay, this one is Big Endian. Little Endian is exactly opposite of Big Endian. So first we store the least significant byte and we follow it with most significant byte. Okay, this one is a difference between Little Endian and Big Endian. Okay, I want to have a larger example which helps us to better understanding of this the difference between Little Endian and Big Endian. So let's have Big Endian, Little Endian, and address. So let's start with address is in hexadecimal. So address is in format 16. Let's start from address 200. Okay, 201, 202, 203, 205, 425, 206, 207, 208, 209, 208, 20B. Let's say we have this memory, and like we have a computer using 32-bit integers. Okay, 32-bit integers. 32-bit integers. So each number is 32 bits. Okay, we want to store two different values, in this memory, in like in big Indian method and little Indian method. What are those variables? The numbers, not variable, number. So the first one is A, B, C, D, 1, 2, 3, 4. The second one is 0, 0, F, E, 4, 3, 2, 1. And the third one is 10. Of course, each of these numbers are 32 bits. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4 is 32. Okay? What about 10? 10 is not 32. We need to convert it to 32. So we can easily say this one is equal to 0, 0, 0, 0, 0, 0, 10. Okay? It's same. So now it's 32 bit. Okay, now let's start storing these numbers in order. First, we want to store this number, then this number, and then this number. In big endian, we start with like most significant bits. So we say A, B, C, D, 1, 2, 3, 4, 0, 0, F, E, 4, 3, 2, 1, 0, 0, 0, 0, 0, 0, 10. This one is where we store our number in big endian. Okay, so this is the first number, this is the second number, and this is the third number. As you see, the most significant byte comes first. Then in least significant, we like reverse the order. So it's 3, 4, 1, 2, C, D, A, B, 2, 1, 4, 3, F, E, F, E, F, E, F, E, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. This one is the way we store our number in little India. But what are the advantage, disadvantage? I'm going to like tell you the advantages and disadvantages. So in big endian, first of all, like the number looks more natural, so is more natural, because in our natural language, first we read or write the most significant byte. For example, here, when I want to write this number, first I will start to write the most significant byte. Okay, it's most natural. And the other thing, the second like advantage is the sign bit. The sign bit for like big endian, for determining. In order to determine the sign of the number, we just look to address with offset 0. So by looking to the first bit of the address with offset 0, which is 200, we know the number is positive or negative. Okay, so then we go to address 204 and look to the first bit. First, if the first bit is positive, the number is if the first bit is 0, the number is positive. If the first bit is negative, then 0, sorry, if the first bit is 1, the number is negative. But in Little Endian, we need to go to, for example, for the first number which is here, I'm just, okay, in Little Endian, in order to see if the number is positive or negative, we should look to address 2 or 3 and see what is the first bit. Okay, so big endian has an advantage that by looking to the address with offset 0, we can easily determine if the number is positive or negative. And the next advantage is that, like integers are string and integers are stored in the same order. Okay, same order. Okay, so when we start from left to right, we store them in the same order, but in Little Endian, they are stored in reverse order. Okay, but what about Little Endian? Does it have any advantage? Yes, it has a big advantage. It has a big advantage that converting, for example, converting a 16-bit number to 32-bit number, okay, not 32-bit number, address, 30-bit address in the memory, 32-bit address in the memory, doesn't require any like arithmetic operations. What do I mean? Let's look here. Number, let's look to the last part. The last part, okay? The value is here. The value is here. And if we want to convert it to another number, let's say add this number with FF00, something like this, okay? And find the effective address. Okay, so if we want to add this and find the effective address, we can simply bring these 2 bytes here and store in these 2 locations. Okay, so now we have FF01. Okay, let's see, sorry, not FF01. We bring them in these 2 locations. Okay, F and 0 10. Okay, so we can simply add our offset to higher like addresses without doing any any addition. But in other case, if we for big endian, we have a problem. We need to actually add those numbers first and then store in the memory. Okay, but in Little Endian, in order to convert the 16-bit to 32-bit, there is no need for any addition. We can simply add the add the offset to the memory location. Okay, so let's continue on our instruction designs. So we have, when we design an instruction, we should know, or we should consider how the CPU will store data. So we consideration consideration is how the CPU will store data. It is a consideration. We need to see and determine how the CPU will store the data. There are three different choices. The first choice is a stack architecture. The second choice is an accumulator architecture. The third choice is a general purpose register architecture. General purpose register is called GPR, general purpose architecture. Before moving to the next part and study them one by one, first of all, let's see which architecture microprocessor uses. Of course, all of us know that the microprocessor always store data from fetched from the memory to accumulator. Okay, so when we say load X, we know that X goes to accumulator. So microprocessor uses the second choice, okay, the accumulator architecture. But we have two more choices, which is a stack architecture, general purpose registers, and accumulator. Okay, so which one, in choosing one over the other, which one we should choose? It depends. It's a trade-off between the simplicity and speed. Okay, so by using a stack architecture, accumulator architecture, we will have simpler hardware. The hardware is simpler. It's cheaper, but speed is less than general purpose register. So it's a trade-off between the simplicity and the speed. Okay, simplicity and the speed. Okay, so we should decide which one we want to use. Okay, so first let's talk about stack architecture. First of all, what is a stack? Let's say on top of your table, you stack books. Okay, so book number 0, 1, 2, 3. Okay, so you stack different textbooks. When you want to put book number 4 on this stack, where you place the book? Do you place under book number 0, on top, or in the middle? Of course, the easiest way and the way we all use is placing the book number 4 on top of the other books. Okay, so this is the stack. And when we want to take a book, read a book, let's just say that we are not going to study the green book. Okay, just when we want to take a book, we need to take the top book first. Okay, even if we want to access to the black book here, first we need to remove the top book, the blue book, and then get access to the black book. Okay, so our access in stack memory is only on the top element top element, and this algorithm is called last in, first out, or LIFO. The last element added to the stack is the first element that we can remove from the stack. Is it clear? The last element from the stack is the first element that we can take from the stack. Okay, so the most important property of the stack is here. A stack cannot be accessed randomly. It means that we cannot access to random locations on the stack. We need to access to the top, top element first. Okay, any question? In accumulator architecture, what about the accumulator architecture? One operand of the binary operation is in accumulator. So here I said we have three different architectures. 1, 2, 3. Okay, so we already discussed number 1 here. We will just introduce, we will discuss it in detail. For number 2, which is accumulator architecture, one operand is in accumulator. Okay, the second operand is in memory if we need to. Okay, like what we saw in Mario processor. Store y. What does it do? It takes the value of accumulator and it stores the memory address of y. Okay, so one operand is in accumulator, one operand is in memory. Okay, so this is the accumulator architecture. The third architecture memory access is GPR, or general purpose register. Okay, so we can use several registers. So we don't have just accumulator. We can have register number 1, register number 2, register number 3, register number 4. We have as many we need. Okay, so we can use them. So if we want to add two numbers, we can simply say add register R2 and register R1 and R2. So there are several registers inside the processor, and we can use those registers. What's the point? It's much faster. It doesn't need to access the memory. Accessing to the memory is the worst thing we can do in processing the data, because it is the slowest thing that the processor has to do. Okay, accessing to memory is very, very slow. So we don't want to access to memory often. So we prefer to have. So faster, it's more efficient, and we can have longer instructions. Okay, because we can have more operands inside of our instruction. For example, let's say like this. It's the opcode number opcode, and we can have operand 1, operand 2, and operand 3. For example, we can say add operand 2 and 3 and put the result in register. Yeah, operand or register, no matter, because operand is stored in the register. So add operand is stored in register 2 with the operand is stored in register 3, and save the result in register 1. So we need to have longer instructions compared to other design. So most systems today I would say 100%, not most, all the systems today are GPI. So they're not using stack architecture or accumulator architecture. They they use like this modern processor. All of them use GPR. Okay, but the GPR itself has three different types to access the memory. So, like in GPR, we have three types. So first type, so GPR. So we have three types of the GPR to access the memories. The first one is memory, which means two or three operands may be in the memory. For example, add the memory location X and memory location Y. Okay? So add memory location X and memory location Y and store the data result in memory location X. So we see that operands are in memory. So it is called memory architecture. The second one is register memory. Register memory, at least one operand has to be in a register. For example, add memory address X with register R1 and store data in register R1. Okay, so add these two and store the result in register R1. We see at least one uh, one operand is in the memory, and the last one is load store, which in fact has no operands. Okay, so like we load and store the data from to the memory. Okay, so the number of these operands and the like number of registers, so the number of operands and number of registers has a direct effect on instruction set length. Okay, the instruction set length is depends to the number of available registers and number of operands. Okay, so uh, now we are going to discuss each of these like architectures in detail. So we have three architecture: a stack architecture, accumulator architecture, and general purpose register architecture. We are going to like see how do they work and one by one. Okay, so first we are going to talk about stack machine and then accumulator and then general purpose register, which we will continue on the next lecture.